Hey everyone, welcome back. Long time no see. All right. Well, thanks for participating in the last one if you did, and if you're new here, welcome to the demos. In the last demo, we kind of built up to the basics of blockchain and smart contracts, coded our first one. But we didn't actually use the technology this hackathon is all based around, Chainlink. So let's dive right into that, introduction to Chainlink. If you missed it in the last one, I'm Zach Ayash. I'm developer advocate for the Chainlink protocol. All right, so today we're going to go through a couple of topics. We're going to talk about the Oracle problem and how Chainlink solves it. And then we're going to go over a couple of Chainlink products, our service offerings. We have the Chainlink data feeds. We're going to be automating smart contracts with keepers, accessing any API we want with Chainlink, and then obtaining a verifiably random number using the Chainlink Vrf. So let's jump right into it. The Oracle problem and Chainlink. Okay, so after the last demo, we talked about smart contract, math-based agreements are awesome compared to our traditional brand-based digital agreements. But it turns out that these smart contracts aren't quite that smart, at least on their own. And their biggest limitation is smart contracts are not able to connect to external data or the outside world, outside the blockchain. So why can't a blockchain just connect to an API, outside data source? Well, remember in the demo before, we were talking about how blockchains, they all have this copy of all the blocks in the blockchain, and they have to come to agreement on what the real blockchain is. This is called consensus. And because of this consensus and the programmability of it all, they have to be deterministic. So this ensures that everyone's able to come to agreement on what the true blockchain is. And if we made an API call, then each node could get different results. So let's look at this image real quick. On the left side, we have the good, nice deterministic blockchain as we know it today. Maybe it's just going to calculate a value, 1 plus 1. All the computers know how to calculate 1 plus 1. They all calculate them the same. They can easily reach agreement. On the right side, we have this non-deterministic blockchain that is connecting to the outside world. And by blockchain, these are the nodes. These are the peers. These are the people running the blockchain software. And so this peer over here, they're trying to call an API. And maybe it's an API that's like, the weather in Charlotte. That's where I live. And so it gets 76 degrees Fahrenheit. This node calls the same API and gets 75 degrees Fahrenheit, just a second later. Maybe the reading on the server changed. Well, now they can't reach consensus. This is why we can't just connect a blockchain to APIs or outside data sources. It would break the consensus of the chain. We can call this the smart contract connectivity problem. Smart contracts, so if blockchains can't connect to outside data resources, smart contracts can't connect to outside data resources, and now we're limited. So this limits smart contract functionality really to only things that can be done within the blockchain, which kind of boils down to the moving of tokens, performing payments, are just kind of representing ownership of things like NFTs. But another way we can call this problem is the Oracle problem. So what is an oracle? Well, in ancient times, the Greeks, an oracle was someone who could kind of tell the future and give you an answer based on any question that you wanted. They kind of knew the truth of the world. And in the blockchain sense, an oracle is a entity or software that knows the truth about the outside world and knows, what the temperature is outside of the blockchain in Charlotte, North Carolina. So any device that interacts with the off-chain world to provide data or connectivity to smart contracts. That's what it is in blockchain land. They can report the results of any outside data or computation on chain. So blockchains can keep their deterministic nature. They're a separate service that lives on top of the blockchain, a middleware, so to say. So now, instead of having the blockchain connect to those APIs, as we saw in the last slide, we can connect to an oracle, which will handle connecting to all those outside data sources. So great, we have a problem to the solution to the smart contract connectivity problem, also known as the oracle problem. We'll create a blockchain oracle. But the naive way to do this is just have a single oracle that reports all of our truths. And this creates if we just make a centralized single oracle node, this creates a centralized point of failure. And remember, when talking about these blockchains, what gave them all their, and smart contracts, what gave them all their awesome properties was the fact that this was like a decentralized system. So we have this highly secure blockchain, decentralized, and but we're triggering events. We're getting data of events to trigger events on the blockchain from a single node, a single point of failure, and that reduces the whole security properties of the blockchain down to that single node. So that's what we're relying on. You know, the end-to-end security of a system is no better than its weakest link, pun intended. In this case, the oracle. So we have this super secure blockchain, no one can hack, and this very hackable central node. What do we do now? We create a decentralized oracle network, or a bunch of decentralized oracle networks. This is Chainlink. Chainlink is designed to be a modular decentralized oracle network for getting secure and reliable data on-chain, and for triggering off-chain events based on-chain conditions. So it can communicate both ways between the on-chain and off-chain world. And because it's decentralized, it preserves all those awesome properties that we love about blockchains and smart contracts. So we bring in data to trigger external computation in a decentralized way. By doing this, we solve this problem by extending the decentralization and trust minimization that we found on blockchains. So we can build a Chainlink network with as many or few nodes as we need to make sure we have good guarantees on our outside data. This is what really gives us the full end-to-end reliability that was the promise of smart contracts that we really wanted to build to begin with. And does it all in a decentralized way. So let's look at this example real quick. We can make a decentralized oracle network, and this would be comprised of Chainlink nodes, just like blockchains are comprised of blockchain nodes. And they're all retrieving the price of a certain asset. We'll say like Tesla stock, for instance. And they all have to get that price, and then they have their own kind of consensus algorithm, just like blockchains do, where they come to agreement on what that actual price is, then post all their observations and their final agreement that they came to onto the blockchain, so we can write some awesome smart contracts around that. So now, by combining on-chain contract code with off-chain resources and oracles, we have what we can call a hybrid smart contract, an even more powerful version of those awesome math-based agreements that we've been talking about this whole hackathon. These are smart contracts that rely on existing on-chain code, combine it with any critical off-chain computations. You know, we've kind of just thought of smart contracts as just code up until now. Now we're kind of redefining what they are. Smart contracts aren't just code that lives on blockchain. Smart contracts is code that lives on the blockchain and anything else we can get access to in the outside world. These hybrid smart contracts truly are supercharged versions of smart contracts. And they're already starting to redefine the smart contract industry as a whole. And they'll continue to go on and continue to redefine how we are doing our traditional agreements. So important thing about Chainlink is it's blockchain agnostic, because it's this middleware, because we have this Oracle network that sits on top of the blockchain. It can actually connect to any blockchain that needs data. And today there's a lot more blockchains than that run smart contracts than just Ethereum. We have of course Ethereum. There's Polygon, Solana, XDAI. You have Rootstock built on top of Bitcoin. All kinds of blockchains, and Chainlink can interoperate with all of them to make sure that they get the most reliable off-chain data that they can have. So I want to start talking about the Chainlink data feeds a little bit. This is a particular service that we can make out of Chainlink Oracle networks. So we talked about in the last demo, we talked about the flaws of traditional agreements. Went through a very specific example, Robinhood, and showed how math-based agreements can solve all of this. Well, in that, I talked about CeFi, or centralized finance, which were these financial digital agreements, kind of traditional, that you would get when you log onto your bank or go to your favorite crypto exchange and do anything financial in today's, a lot of the most popular applications today. Well, DeFi is totally redefining that market. DeFi, unlike CeFi, centralized finance, is decentralized finance. And it's taking all of these traditional financial digital agreements and making them decentralized financial agreements, putting them on a blockchain. This provides those also properties like transparency. So now we can look into the exact how these DeFi smart contracts are written and see the exact code that's written in that contract. Gives you control of your assets. No bank or exchange has to custody your funds. And you can even, like, these DeFi apps are even giving some awesome yield compared to, traditional savings account, And my savings account, I think I get something like 0.01% interest. And certain DeFi apps, they're giving 5%, 6%, 7% interest, in part because of the all these awesome efficiencies that we're creating. So we're getting all these awesome advantages of DeFi and redefining how we're looking at finance and decentralized financial digital agreements and kind of replacing it. But the thing is, a lot of these DeFi contracts, financial contracts, they need to know price data. They need to know what the price of certain assets are. So if you wanted to build an exchange, on chain, this exchange would have to know what the price of all the assets are that exist outside of the chain. Ether exists on chain, but even the Ethereum blockchain doesn't know what the price of Ether is in dollars. Dollars is this concept that's kind of outside the blockchain. And so to do this, we can create a Chainlink network, a decentralized Oracle network, or DON, that will grab the price data of all of these assets that we want to represent on chain, and it'll pull them in that trustful, decentralized way. And so you can kind of look at this diagram, and we have all these centralized traditional CeFi exchanges here. Maybe these are all crypto exchanges, and you have data providers that aggregate this data. And then you have our Chainlink decentralized Oracle network, which connects to these data providers and maybe even some of the exchanges themselves. And they themselves, each node, they'll aggregate that data to achieve what they think is the true price of that asset, what they calculate is the true price of that asset. Then they'll share among each other and come to consensus. and aggregate their own answers to come to a final guaranteed truth about what the price of that asset is. And they'll post it on chain here that into what we call a reference contract that any kind of other application that's built on the blockchain can use. Now, we can build these awesome DeFi smart contracts and primitives that take advantage of this price data. And it really lets us take it to the next level. So why are we harping on why we need to use decentralized Oracle networks or DONs for these Oracle functions? Well, there's already been plenty of attacks on smart contracts in the blockchain space that targeted specifically centralized oracles. Like we said earlier, a centralized oracle makes a pretty easy attack target. And these attacks have lost users and creators tons of money and reputation. That's not cool. If we have in crypto, since everything is open, if you have something that can be exploited and money will go into it, and in crypto, money flows fast, someone will find an exploit and try to take that money. So we can actually go to data.chain.link and we can view these decentralized Oracle networks live, posting data for a whole bunch of different data sets. So here, we have cryptocurrency data sets. We have a bunch of different chains we can go look at. Right now, we're on the Ethereum mainnet. So, let's look at ETHUSD. All right, the trusted answer. This is the answer that all the nodes most recently came to agreement on. It's saying $4,036 right now. And these are all the nodes that are working to get this data. There's a lot of them. And, they're all doing their own aggregation, like I mentioned earlier, to make sure that they post the best possible answer. Because we can see each answer. You can look at each node and see the individual answer that they posted. So if a node starts acting a little funky and they want to post 400 instead of 4,000, that's all going to be visible. All these nodes have their reputation at stake, as node operators. We can scroll down, we can see the price history, and we can look at the individual nodes and what they've been posting, their Etherscan addresses, all this awesome information. And we can even see the users. Look at how many DeFi apps are using this data to do cool stuff. And, they actually sponsor some of this data. They're getting a lot of value out of this. So they help pay and secure all of this data being posted on chain. So yeah, that was data feeds. We just went over that. Each node aggregates their own data, and then that data is aggregated within the nodes themselves to get the final answer. So let's just go ahead and jump into a demo and see what programming with these data feeds is like live. So again, you're going to see this a lot. What do I have installed? What do I have? We're just going to need a MetaMask wallet. We're going to need some testnet ETH, and we're gonna go ahead and start at the Chainlink Docs this time. So from the last demo, I already have some testnet ETH in my wallet. So we're good to go. If you need a refresher, please feel free to watch the last demo I did to see how we got all that set up. Okay, so let's go ahead and go to the Chainlink Docs. Okay, so this is the official Chainlink documentation. It's all open source, a really great resource if you ever want to do anything Chainlink and really smart contracts in general. But we're just going to go right now and we're going to look. We have an introduction section on the left nav bar, and we have a section called Using Data Feeds. So we click on Introduction to Data Feeds. It's going to give us a quick explanation of how data feeds work. We're going to go ahead for this demo, and we're going to go ahead and go to Get the Latest Price EVM. So we're going to do this all on Ethereum for now. If you want non-EVM chains like Solana, they're being added. So right now we have another one for Solana. We're going to focus on EVM, Ethereum for now. So it tells us where these data feeds are available. And look at this. It gives us some completed demo code that we can use to get the latest price. We're going to use the data feed to get the latest price of ETHUSD and put it on use it in our smart contract. And if we keep scrolling, you'll see a button, deploy this contract with Remix. Let's go ahead and press that. Okay. And all right, we're back in Remix, and it automatically loaded up that code for us. Let's go ahead and zoom in a bit. Full screen. Okay, cool. Okay, so here we have that smart contract. And just like in the previous demo, you'll see a lot of the same terms. The pragma. Something new here is the import statement. This means it's pulling code from somewhere else that we can use in our smart contract. In this case, it's pulling in a file called aggregator v3 interface.sol. This allows us to interact with price or data feeds in our smart contract. So again, we define the contract name. We have our state variable, calling it price feed. It's a custom type called aggregator v3 interface. It's taking that from this import statement. We have our constructor, which initializes our state. And this time it's pointing to, it's taking that aggregator v3 interface and pointing it to the reference price data for ETHUSD on the Kovan network, the test net. So everything's kind of set there. And we have one function, get latest price. And it's going to call that, and it's going to recall this function from our price feed that we set here. And it's going to call another function on that called get latest round data. And get latest round data is going to return all the information about the latest round that decentralized Oracle network posted data for. It's going to tell you the round ID. It's going to say, hey, this is the actual price. Tell you when that round started, the timestamp of when the data was posted, and giving you the data of what round that data was put into the blockchain at. And then what really all we're going to care about is the price right now. So it returns price. Great. So now we're going to, we have our smart contract. It's using the Chainlink data feed. We're going to go ahead and compile and deploy this. So let's go ahead and compile it. Let's turn on auto compile again. All right, so everything is working fine. We get a couple of these informational warnings again. Again, if it's yellow, no need to worry about it. It's saying, hey, unused local variable. We're not using any of these other things that we're returning. We're only using price. But that's okay. That's all we need for now. So nothing big. No red warnings that say, hey, the compiler is not able to read this code. So let's go ahead and deploy this. Now remember, this is set up for the Kovan testnet to get us going. So we're not going to use JavaScript VM. We're going to switch to injected Web3. That'll connect us to our MetaMask again. Say connect. Make sure everything is good there, and it is Remix. And our MetaMask is set to Kovan testnet. And so that's what our Remix is reading, Kovan testnet. It's looking at the right account. It shows my ETH balance there. That is indeed my account. Our gas limit, we're good there. And we want to make sure that we're pointing to the right contract. You see, now there's two contracts here because it's loading in this contract from our import statement right here on line 4. That's not the contract we want to compile. We want to compile our price consumer v3 contract. This is the one we wrote, and it includes that other contract that we're importing in. Our constructor doesn't take any arguments. We're good there. We can just deploy it. We are deploying, so MetaMask is going to come up, say, hey, you're changing state on the blockchain, going to cost some gas. We're all good there. Confirm, and boom, that was quick. We have our contract. So now we can click get latest price, and it should show us the latest price of Ethereum. And bam, it shows us the latest price of Ethereum. There's no floating point decimals in Solidity, so it gives it to us as integer 256. There is a function that tells you where the decimal point is, but this is how we can access price feeds or data feeds from within our smart contract and start building all kinds of cool stuff. So now we can use this method and start making some cool contract logic around it in our contract to do cool stuff. And so that was basically just a basic introduction of Chainlink price feeds. Again, if you ever want to know more details, the docs are a great place. As you see, I basically just went straight to the docs and follow the demos here. Our demos, we put a lot of work into. They're really great. I still use the demos all the time. And we're going to continue doing that throughout this demo. So if you have any questions about price feeds, any details, you can read the docs. We can figure out how to get historical price data. There's a registry of where all our data feeds are, all kinds of great information, and some contract, some chain-specific addresses. Where our addresses on Ethereum, and on the hackathon, they'll probably be posting a lot to test nets. So you have Kovan test nets, Rinkeby test nets also here. Well, I think Rinkeby is also here. Kovan is awesome though. I love testing on Kovan if you can. But yeah, you can also have Binance Smart Chain feeds, Polygon, XDAI, Huobi, EcoChain, Avalanche, Phantom, Arbitrum, Harmony, Solana, and Optimism. So we go, if there's a data feed, you can find it here, and you can find all the addresses to use in your smart contracts. Awesome. All right, so let's go ahead and before we move on, do we have any questions? I'll take a sip of water. Can we use any API with the data feeds? That's a great question. So the data feeds are already these curated, decentralized Oracle networks that do all the heavy lifting for you and connect to all the APIs and do the aggregation that we talked about. So there's some data that you need to get and isn't available in the data feed. We can actually use the Chainlink Any API solution. A lot of people opt to use this for their hackathon. It's a great way to MVP your application. We're going to go over that later. So if you want to connect to any API, we will handle that. Let's see. A little confused by the syntax of get latest price function. All right, let's go back and let's look at that again and kind of go over the syntax. So, first, I'm just going to go through it. So, all bases are covered here. We say function that defines that we are writing a function. Get latest price, that's just what we're going to call it, the name, right? And it's not going to take any arguments. We're just going to use this to read data. And we're going to make this function public. So any account or any other smart contract can actually call this function. We're going to say view. Say, hey, we're not actually accessing state, or we're not writing anything to state. We're just going to read data from state. So we're not actually going to do really any hardcore computation. We can label it view. That makes this function gasless. It doesn't cost any gas. And finally, we're going to say it returns an int, and we'll define what that int is going to be, but this function in general returns an integer. And so we put our curly braces. This is where we put the body of our function. And, to make this a little easier to read, for right now, I'm just going to cut this out. So now we're saying, hey, I want to call this variable price feed, which we defined and initialized in the constructor. And we're going to call latest round data that comes from that variable. And that's going to return a bunch of values when we call that, not just price. It's going to return a bunch. So we need to take those values and we need to put them in some kind of variable and store them so we can use them. That's what we're doing here inside the parentheses. So we're saying, hey, get latest round data is going to return a bunch of data. Take the first unit of data it returns and store it within round ID. Take the next unit of data it returns and put it in price. Take the next, so on and so forth, and stores it in there. And finally, we say, hey, all we really care about in our smart contract is the price. So we stored all that data, but really, we're just going to return the price. And these data feeds do put in, like the price feeds are put in as integers. And again, remember, int is synonymous with int 256. So there you go. That's kind of the structure of that function. What's the name of that data structure? An array? No, this is just a bunch of different variables all together. We're just kind of creating these variables in memory in the function and storing them there. Okay, I think these feeds are sponsored, but will they at some point become non-public unless you pay for it? Great question. There's no plans that I'm aware of at the moment to make these feeds non-public. We know how important these feeds are to building these important DeFi primitives, and we want the space to continue growing. So for now, they are public. Okay. Last question. Okay, 2 questions, actually. I'll take these 2. What restricts the Oracle nodes from providing wrong data? Again, that whole aggregation property and their reputation. There's all these this whole subject of designing these systems called crypto economics. How do we incentivize actors in this distributed system, this decentralized system, to act in the best interest of the users and the important parties that are using it? And so, you can go into a lot of detail. There's a lot of good resources online. You can Google on how, Chainlink is secured through crypto economics. But in a nutshell, they all have to go through this consensus algorithm. They all have to figure out what the truth is. They're all aggregating data. Remember when I showed you data.feeds.link, all their reputations are on the line. Everything they post goes on chain and is available forever. And, the link token comes into account and, kind of keeps them in check. So in a nutshell, that's how these kind of nodes are restricted from just providing any data. And finally, can we have current time as a data feed? We can make a data feed for anything that exists, any kind of data that these nodes can access. So basically everything. I don't think the current time is a current data feed. It's certainly one you can make. So all of this software is open source. Chainlink is open source. So anyone could make a feed. The Chainlink Labs team can help make a feed, if there's a lot of demand. But we can make a feed for anything. All right, let's go ahead and move on in the presentation. All right, so we're done with data feeds for now. Let's go ahead and move on to the next thing, which will be automating our smart contracts using Chainlink keepers. I kind of want to put this early on because this is one of the newer services that Chainlink enables, and really shows how powerful this Oracle paradigm can be. It doesn't have to just be about getting data and putting it on chain. I mean, we can do all kinds of crazy off-chain computations, and we'll go into what Keepers does. So another thing that's kind of limiting about smart contracts, and we talked about that Oracle problem and how they can't connect to outside data and resources. But blockchains can't actually really execute their own code arbitrarily. They need an outside actor to initiate it, right? So, as we've been deploying our contracts, if I want to run get latest price, I have to click that button, get latest price. I have to run that code. We have to run our functions. And so Chainlink Keepers allows us to create a decentralized Oracle network that will arbitrarily run our code whenever we want. We can define the conditions. We can even define some computation that the keepers will do. And then they'll execute our functions when the time is right, when we define they should run the functions. Of course, it's a decentralized Oracle network, so it does so in a decentralized way, preserving those awesome properties of the blockchain. So one example of where this is useful is in DeFi loans. So back to DeFi. Almost all loan applications in DeFi are what are called over-collateralized loans, meaning that when we put assets into DeFi and want to take out a loan against those assets, we have to actually put up more collateral in terms of like US dollars, for example, than or ETH in there than the loan that we take out is worth. And if that collateral's price, and that price is being determined by Chainlink data feeds, of course, falls below a certain price point, those loans need to be liquidated. Someone has to take out that collateral and say, hey, look, this loan isn't working out. I'll pay back that loan and I'll take out that collateral. But traditionally, you kind of just hope that people will liquidate the loans and that this will happen. And in times of high gas fees and chaos, when the markets are going insane, this can be tough. It's, gas prices skyrocket. Gas prices can go above the gas costs. People are just like kind of panicking. So we can, employ the Chainlink Keepers network to come in, monitor those loans, and liquidate them as they need be, making sure that these financial systems don't break down. It's not in here, missing one slide, but another cool use case for keepers is time-based smart contracts, which we're about to do in the demo. So maybe you have a smart contract that wants to run every hour or every day. These we could use the Chainlink Keepers to run that function on a timely cadence. So now, again, let's learn by doing. Let's hop right into the demo. So what do I have installed for this? I have MetaMask wallet, I have testnet ETH. We're going to start with the Chainlink Docs. We are missing one thing, though. We're actually going to need to get testnet link now. So just like ETH, Ethereum requires ETH for gas. The Chainlink services require link tokens to pay for the computational resources that the link nodes are going through. The data feeds are sponsored, which means that the users and the big DeFi apps that are sponsoring them, they pay those feeds for the users to keep an open ecosystem so we can continue building awesome DeFi apps. But for something like the Chainlink Keepers, we're going to need to get Link to pay for this service. So I actually don't have any Link in my MetaMask right now, only ETH. So we're going to go ahead and do that. So where I have testnet ETH, we're going to click on that because it's going to take us to the Chainlink faucet, faucets.chain.link. And instead of just ETH, we're going to get some Link this time. So we'll get our public key, our address, and we'll put in our address, pass the CAPTCHA, not a bot, and ask for link. All right, so we have 10 test link on the Covan testnet. Great. It gives us the transaction hash to show. Go to MetaMask. What? No link. What's going on? Yeah, so MetaMask, remember all these ERC20 and in Link's case, ERC677 tokens are smart contracts. MetaMask can't feasibly keep up with all those smart contracts that exist on Ethereum. So we need to add the Link token contract address here. It'll know where to look. So to do that, we're going to go back to the docs. So we're just going to go to type in docs, chain.link, and I'm already here. Just want to type it in. And we're going to scroll down, and we have developer references here. Here we can see Link token contracts. This is where all the Link token contract addresses are stored for all our chains the Link token exists on. And we see here we have Ethereum mainnet, Covan, RinkB, Gorelli, other EVM compatible chains, you name it. We're deploying everything on Covan. So we're going to take this address and we're going to copy it. Control C or Command C for my fellow Mac users. So, and also it gives us a handy link because it knows probably if you're here, you're going to want to get some funds from the faucet. So we're going to go on our MetaMask. We're going to click import tokens, and we're going to paste this address into the token contract address. So it's reading that smart contract, says, hey, I know this is Link. So many decimal places are there. We'll add custom tokens, and look, it's showing that tin link. So click import tokens, and now my wallet will display my Link tokens as well as my ETH. Great. So good there. And we'll head back into, we'll leave Remix for now. And we're going to go back. And so now we're going to start the demo. We're going to use Chainlink Keepers, and we're going to automate our smart contract. So functions will run in our smart contract, even without us having to run them. So first, again, start at the Chainlink Docs. Boom. Back at the Chainlink Docs. Docs.chain.link. Come here a lot. And we're going to go to using Chainlink Keepers. Again, there's a little introduction here that explains to us the value of Chainlink Keepers and how it works, and gives us a little detail on how we need to onboard. We're going to go ahead and go to making a Keeper compatible contract. So there's two major parts to making Keepers work. We need to make our contract be able to work with Keepers, and then we need to actually go to the Chainlink Keepers contract itself that determines all the jobs that Keepers work with. We'll get there. So making Keeper compatible contracts. Again, if we scroll down, it gives us some code, and then finally an example contract. Again, we can deploy using Remix. So let's go ahead and click deploy using Remix. All right, so again, we already have our setup smart contract. I'll skip, going through the beginning. We already know pragma, import, contract, state variables, constructor. But now we have two particular functions that are too big, that are unique to smart contracts in general. We have check upkeep and perform upkeep. So these are two functions we're going to need to put into every smart contract that is going to interact with Chainlink Keepers. Check upkeep is going to tell our smart contract, and it's going to tell the keepers when they should actually perform the work they need to perform, when they need to call perform upkeep. So check upkeep actually doesn't ever need to be called by any users or the developers themselves. Check upkeep is just for the Chainlink Keepers. They're actually going to take this function and they're going to virtualize it on their own nodes, and they're going to run it there until the conditions are met. So it's not actually going to cost any gas, but we need to include it. In this case, the upkeep is, we say, is upkeep needed? So we need to return a bool, true or false. Is the upkeep needed? And we're going to say, hey, we're going to access this inherent variable on block.timestamp. This is going to say, hey, what time was the latest block created? And if we subtract the current block timestamp from the last block's timestamp that was created, and it's greater than a certain interval we define, and we're going to define in the constructor, then perform upkeep. Then, so let's say, all right, our block timestamp and our block timestamp minus the last timestamp ends up being greater than the interval. The Chainlink keeper will see that, say great, and it's going to run perform upkeep on this contract. And we can pass in call data. So like if we want to customize each run or of our upkeeps, we can actually tell it, hey, like actually we want you to pass in this data into perform upkeep. We'll call it call data. Doesn't have to be used. And that'll pass in data to the smart contract, and we can do some cool stuff with that. And we can actually have, within check upkeep, we can have the keepers nodes do computation on that data before they post it. So, okay, great. Let's go ahead and deploy this contract. Again, everything's compiling okay. Just a couple of informational warnings, nothing red. We're going to switch to injected Web3 again because we're going to deploy this to a testnet. It's connected to my MetaMask already. Kovan, great. Right account. And again, make sure it's pointing to the right contract. We don't want the interface. The interface is what we're importing. We want to say counter. In counter, our contract has a constructor, that update interval. So when we deploy this contract, we have to tell it like, hey, what's the update interval? And then we're going to use that again for the keepers to say when they need to perform upkeep. We're going to store it in this state variable interval, and this is an immutable state variable. So let's put it there. It's not going to change. And, we have last timestamp. And we have counter. So, we're going to initialize our counter at 0. Every time we perform upkeep, the keepers perform upkeep, it's going to increment that counter by 1. And so we need to define our constructor. How often do we want the keepers to perform upkeep? I'm going to say every 10 seconds. We'll put 10. This constructor is a unit. All right, we should be good. Deploy, we're pointing to the right contract, not the one we're importing. Pay our gas fee. All right. Our contract is deployed to the Kovan testnet. And if we click on counter, it's at 0. So where we started it out at. If we click on interval, it's at 10. That's what I put in. So 10 seconds is what this is defaulting to here. And so every 10 seconds it'll check. And the last timestamp, we'll just get the block timestamp that we deployed this at the constructor. Cool. All right. Now we've deployed our keeper compatible contract. We're all good there. We need to now go to the second part of this and register it with the keeper registry. Guess what? We're going to go back to the docs and figure out how to do that. Register upkeep for a contract. This is part 2. And again, if you forget all these steps, you can go to the introduction. It explains everything. These will walk you through all of this. And so this is still all done on chain. We're going to say, we need to tell the keepers now that we deployed our contract, it's good to go. Like we need to tell the keepers, hey, this contract exists and you need to start looking at it and performing your keeper duties. And so we're actually going to, and all this is done still on chain in a smart contract where we can say, hey, this is the address of our contract. But, there's this convenient Chainlink Keepers app we can go to, which will help us go through this whole process. And, see some information about Chainlink on mainnet. And we see some buttons, and we can see some contracts that are on Chainlink Keepers right now. Right now, we have it pointed to Kovan testnet because that's what our MetaMask is on. So you see a bunch of nonsense, test upkeeps that people are just kind of testing out their code and making sure everything works fine. You can switch to Ethereum mainnet and see some, really cool legitimate projects that are using Chainlink Keepers. Live now. Back to Kovan testnet. That's what we're working on. And we're going to click register new upkeep. You must connect your wallet before adding a new upkeep. So my wallet is not connected. And you'll see up here in the top right, there's a button for connect wallet. So click that. You'll see it's communicating with our MetaMask. We see this is indeed keepers.chain.link. That's what we want to talk with. Hit next. They just want to see our addresses. Cool. All right. We're in. This is my wallet address here. Let's go ahead and start registering that new upkeep. So we're going to have to put in, an email address, an upkeep name, an upkeep address. I'll just put in one of my old deprecated emails for now, a Yahoo, and we'll call this Hackathon demo. So that's what we'll call this upkeep. Now we need the upkeep address. This is the address of that contract we just deployed. So where can we get that? We had it in Remix, right? So if we just go to Remix again, we have the address here. We click on this double page icon. That copies the address of this deployed contract. And come back here. We can paste that in there. The admin address that has control of this upkeep, it defaults to my wallet that I'm doing this with. That's what we want to do. A gas limit. So the keepers, they're going to be running all of these functions, and that's going to cost them gas. And, we're paying for these keepers. Now, those gas costs, since we need it, we're paying for them. We're sending this in terms of link tokens to the keeper nodes. And so, if the gas gets expensive, our keeper's upkeep gets very expensive. And so we may want to put a gas limit on a gas limit so that the keepers don't get too expensive if something happens with our computation and it gets too expensive. If we go to the docs, it kind of explains more on how all these fees are calculated. You can read it here. But for us to say the gas limit is we'll just put in 200,000. Yep. Okay. And if we wanted to put any check data in there when we run check upkeep, we could. We're not going to today. And we needed to start funding our contract with Link. So we're going to pre-fund it. So every time these keepers run our functions again, they're going to look at how much gas costs it costs them. And there's this formula. Again, you can read in the docs. And then they're going to take out some of that link and get paid. Right? So we need to pre-fund it so they can continuously run their functions. And let's go ahead and let's put all 10 of our link in there. We can always go back and get some more link. So we'll register upkeep. And it's going to ask me to confirm again, pay the gas. We're going to have to pay some gas to register it in the first place. And it's going to wait and confirm. Awesome. So our Upkeep registration has been submitted successfully. It's on chain. And here's the transaction. And we can actually view that Upkeep. Okay, so it's active. It gives us the address. Here's our current balance of Link we pre-funded it with, and some details on the Upkeep. What our ID is, when it was added. My wallet is the admin address, and the gas limit we set. It'll also show you the address of the last keeper that ran your Upkeep. But you'll notice something. We're getting a warning. This Upkeep is underfunded. If you are the owner, consider adding funds. So to make sure that the keepers are always getting paid when they do their Upkeep, we don't want the balance to fall to zero. So it is required to put in a minimum balance of Link to make sure it runs. I only had 10 Link, so we're actually going to go back and we're gonna go back and we're gonna get some more Link, so we can hit that minimum balance. We can always go to Link token contracts, and it'll link us to the right faucet for the network we want. So we'll go ahead and go to faucets.chain.link/Kovan, and send me 10 more Link. Oh, gotta put in my address. Okay, so this will get us some more Link. Great, we have 10 Link again. So now let's go back to the Upkeep, and we can click on the button right here, add funds, to make sure we get above that minimum balance. Let's actually add in 8 more Links. So we'll have 18 Link. It can run maybe a couple of times. And we'll click confirm. Now we actually have to, send that Link over. And it's going to go through a bunch of confirmations, allowing it to run. All right. So my Link token got sent over. Now we have to confirm everything again with the keeper's contract this time. Say, okay, good. All right, our funds were added. And look, it looks like it's already running. We already had a keeper that fast. Now that we've hit the minimum balance, run. So let's go back to our contract. Let's see what's been doing here. All right, remember, what are they doing when they perform Upkeep? All they're doing is, every time the amount of seconds passes, they check it, they run perform Upkeep, and they increment our counter by 1. So we have counter equals counter plus 1. Now our counter was initialized at 0. That's what we're still showing down over here. If I click on it now, hopefully it should have incremented some. Let's see. 4. It's already run 4 times. Awesome. And now every 10 seconds, these keepers will keep running, and they're going to run through my Link balance, and they'll keep running. Maybe we can come back at the end of the demo and see how many times the keepers have run. Awesome. So that was Chainlink keepers. That was automating our smart contracts, using them. Let's go into the comments and see if there's any questions. Question: why is a check upkeep function not having a return keyword? Let's go back there and let's look at check upkeep. The reason it doesn't is because we're not actually returning anything in this function. We're not. It can return a bool, but remember, the check upkeep is something really for the Chainlink keeper nodes to run. We're never going to have to interact with this, so it's not too important. How often should I deploy to a testnet? Henry here. Looking for a best practice in this question. Is Remix robust enough to write complex smart contracts and fully test them without deploying them to a testnet? Oh, awesome question. Remix is great, especially when you're starting out. It's great to quickly get a quick win, go in there, deploy your contract onto a testnet, see how it works. But a lot of the power in developing smart contracts is done locally in these like deployment frameworks. So you have Hardhat, Brownie, and Truffle. Those are three of the biggest ones. And that's where if you get a little bit more experience with programming, you can mess around with them. That's where you can really write robust tests. You can all locally. You don't have to do it in your browser. You can fork the blockchain and make a local instance and test it there and write all these awesome scripts to automate everything. That's where most developers actually do a lot of their work when they're developing like production grade smart contracts. And we conveniently have these starter kits that already come preloaded with a bunch of like some initial tests and like Chainlink smart contracts. If you want to see them, you just have to type in GitHub. Wrong browser. Let's do it over here. Let's type in Chainlink GitHub. We're going to click. You can click on this. This will take you to the main Chainlink, node stuff. But we're actually going to go to Smart Contract Kit, the organizational account here, and we're gonna click on one of these. We'll click on Hardhat Starter Kit up here. You see, there's also Truffle Starter Kit and Chainlink Mix, which is a Brownie Starter Kit. And so you can work with one of these. And if you already have some experience, we'll talk about a little bit about them later. But these are great places to go. Feel free to clone, fork, whatever you need to do, and work with your smart contracts there. Constant Crypto, yeah. I see like using Truffle and Ganache. Those are awesome choices to do things locally. Can you explain again the input parameters of the keepers function? Yeah, so we have this bytes call data, right? So or check data. We can tell the keepers, like when we were registering our upkeep, we can tell the keepers, hey, like here's some check data, go in there and we can, every time we make a new upkeep, we can customize it for different inputs. So maybe I have this one contract and I want an upkeep that starts with a check data parameter of 0, and then another upkeep registry that starts with a check data of 1. Then these the keepers will start the check upkeep with different initial conditions, and can even work and use that data to do some cool stuff, and then pass that data on to perform upkeep as call data. So then we can make one contract, deploy to the blockchain, and then have multiple upkeeps that start with different initial conditions and maybe even do different off-chain computations. Awesome. Great questions, guys. Let's move on. So we've already gotten some questions about this. So let's go ahead and move on to accessing any API using Chainlink. Again, this is a powerful tool if you just want to get MVP for some data that isn't already on a Chainlink DON, Decentralized Oracle Network, or you don't want to go through the effort of, because it's quite difficult to spin up can be quite a lot of effort, I should say, to spin up a Chainlink network. So yeah, we can connect to any arbitrary API using Chainlink. We call the solution any API. cleverly enough. And it could be anything. It could be a web API, enterprise system, database, Internet of Things censored, or an API-enabled physical device, such as a car. There's a cool hackathon winner who now works on my team, Harry, who actually connected a smart contract to a Tesla. So that's awesome. So you can find a bunch of nodes that to do this work. So we do this by going through a node. We go back here. We do this by going through a Chainlink node that can relay this information back and forth between the blockchain and the real world. And if we want to find these nodes, we can go to a great website, market.link, where we can find a bunch of different Chainlink, what we call jobs, adapters, data sources, feeds, basically a lot of different things for the Chainlink network. But in this case, we can find nodes that will do our work for us. And we're going to talk about nodes and jobs in a second. But just to give you an overview of market.link, let's click here. And so, yeah, you see here, we have market.link. You know, we can say, hey, like I'm a data provider. I want to list my data here. I really need this particular data. We can request some new data. I'm going to go here and click on nodes. And we have a bunch of networks here. And these are a bunch of Chainlink nodes. Some of these are in our, some of these are in the feeds, like in the ETHUSD feed we were talking about. And, you know, we can click on them. Now let's look at link pool. Now you can see some metrics on these nodes, the kind of jobs that these nodes will run for us, a bunch of good stuff. And if you want, anyone can come here and they can list their node and their jobs. We'll talk about adapters in a second. All right, so any API. We're going to go ahead and go through the demo. You already know how it is. We're going to go through, and I have my MetaMask wallet. I have testnet ETH and testnet Link stored in my, because we will need Link. From here on out, every service other than data feeds is going to require us having Link. Maybe I need to stock up though. And we're going to start at the Chainlink Docs again. Back to docs.chain.link. This time, we're going to scroll down till we see using any API. Again, we get an introduction explaining how this works. We're going to make a GET request, though. So one of the most simple things we want to do is we just want to make an HTTP GET request to an outside API, and we want to see what data it returns and post that on chain. All right. So let's go ahead and deploy this contract using Remix. Close out some of this. Keep our faucets open in case we need it. We'll keep our keepers. And we'll close this Remix instance. Okay, so we have our API consumer contract now. That's what we're going to call this, the API consumer. And, it imports Chainlink client.sol. So just like we had an import for keepers to interact with keepers, to interact with any API, we need to import Chainlink client. And we're going to say, hey, this API consumer inherits from Chainlink client. So if you're used to object-oriented programming, that just says, hey, this is taking in some of those methods of this parent class. And, we have a couple of state variables, volume. So we're actually going to use this any API solution, get the volume of ETHUSD from an exchange or a website. And a couple of state variables, Oracle, job ID, and fee. So this is what I'm going to explain to you what these are. So remember in market.link, we were looking and I was showing you about all these different Oracle nodes that are listed. These nodes have an address associated with them that actually represents that node on chain. And so if we want to make a request through that Oracle, we need to know the address, the Ethereum address that represents that Oracle on chain. That's what the Oracle here is. And then job ID. So that Oracle that specific node may do multiple things. It may have a job to get a GET request from any website you want. It may have a job for a very specific website. Like, hey, this is a weather data aggregation job, and it just does that. And yeah, so it can have multiple jobs that do many things. And so we need to define a job ID. And so when nodes go on market.link and they list themselves on like, hey, this is my node, this is my address, they'll also list the job IDs they have and what those job IDs do. And finally, a fee. So again, we're requesting something from these nodes. We need to pay them in Link token for the work that they're doing. So this is the Chainlink network. Okay, so real quick, I actually just want to show you a job. We'll go back to market.link. We'll go to jobs. Like I was saying, you see all these different jobs and what networks they're on and what node is running on them. And so this is for on the Ethereum Rinkb testnet, some Instagram impressions job. That's pretty cool. You know, copy some data, multiplies it, gets the number, and post it on chain. That's cool. Gets Instagram impressions. So you really can't do anything with these any API requests. All right, so we're gonna go back, like looking at the code. So we initialize this demo code we have in the docs, automatically initialize us to a specific Oracle address and a job ID. These are already set for the job we're gonna do, which is just make a GET request. And the fee is set. We only need to pay 0.1 Link to get there. So then we have our function, request volume data. This is where we're going to send a request to that Chainlink node and say, hey, I want you to grab us some data. It's public. Anyone can run it. It returns a bytes32 called a request ID. We'll get there. So first, we need to build the request. We need to tell that Chainlink node where we want to go to get the data and how to get it. So we'll do request.add, and we'll say, hey, we want to make a GET request, and we want to make it to this URL. So this is actually an open URL. If I make this GET request, if I just push this on my browser should make a GET request to it. And we return all of this data in JSON format. And so, yeah, we're saying, hey, make a GET request, send it to that this URL. Then we're going to say, remember that big list of data? That's a lot of data in there. We need to tell what data we want to extract from all that JSON object. So we're going to say, hey, we're going to say the path for the JSON is this. It's going to go through that JSON. It's going to find raw, then go into the value for there, and it's going to find ETH, go to the value for there, USD, so on and so forth until it gets to volume 24 hour. So it's going to extract that particular data value that's within volume 24 hour. And then we're going to take that and we'll say, hey, we want the node to multiply it by a certain number to get rid of the decimal places. And then, you know, we'll actually add that to our request, and we'll return the actual function that sends this request out to the Oracle. And this function comes from that import Chainlink client. So say send Chainlink request to. We'll put in the Oracle address. This request that we've been building with request.add, where this continues to build a request. So this will send out our full request. And what we set to be the fee, 0.1 Link. When this function runs, it actually returns the ID of that request, the request ID, and that's in bytes32 form. So that's why we have a return here for bytes32 request ID that we're calling request ID. When this runs, so the compiler will run this code here and say, okay, replace this with the request ID that gets sent out, and it'll return it. Awesome. So that's what will happen. And then we have fulfill. So just like keepers, they have to have a function to run after we send the request out. This node will then will send data to this fulfill function. And so that'll run this fulfill function here. And pass in that request ID. This should be the same request ID that was generated when we made the request, and the actual answer. In this case, the answer will be uint256, and we'll call it _volume. This is public, but we have this what's called a function modifier that comes with it that will help make sure that our Chainlink node is the one that fulfills this function. Okay, so that's basically what's going to happen. We're going to send out the request by calling this function. The Chainlink node will then do its work and fulfill that request by calling this function. And it will take that data, put it in volume. It will take volume and we'll store it in our state variable called volume. So we will now go to the compiler. Compiler is giving us a green check mark, not even any warnings. And again, we'll make sure we are pointing to the right contract. Our list is getting kind of big now. API consumer, that's the name of our contract. API like that. API consumer. And we'll go ahead and deploy. We don't have any arguments or parameters for our constructor, so we can just straight up deploy it. But I deployed it to JavaScript VM. That's not going to work. We want injected Web3. Okay, API consumer, deploy, confirm. Awesome. So our contract is now deployed down here. And we have our volume, which initialized at 0. We didn't set anything to initialize it with, so it defaults to 0. And we have a request volume method and fulfill method. We're not going to actually call the fulfill method. We'll never need to call it. Just like perform upkeep, this is for the Chainlink node to call. So let's request volume. Gas estimation. Yeah, so remember, we need to pay the Chainlink nodes and link tokens. So we need to actually fill the contract itself with link tokens to get this to work. Because in the contract, we'll say, hey, I can package this link token and send it over to the Oracle. So yeah, we'll go ahead and not send that transaction out. And the first thing we're going to do is we're going to copy the address of our deployed contract. We're then going to come here to our account and we're going to click send. And we're going to paste in that address up there. We're then going to switch from ETH to link. And, it only costs 0.1 link to send a request. We'll give it a little bit more. We'll say 0.3. My MetaMask is just estimating at 0.299. And we'll hit next. And pay the gas fee to send link, confirm. Now we have to wait a second for the link transaction to go through. This is, the disadvantage for using Kovan. It takes a little time, compared to local environments or JavaScript. So our link is sent. We should be good now. If we hit request volume, what happens? That error went away. We're good. It's giving us the details, how much estimated gas fee we're going to need to pay. We're going to go ahead and confirm that. Great. Our request is sent. It's been included. Let's check the volume. There's nothing there. It's still 0. Why? Because remember, we're sending this request to a Chainlink node. That Chainlink node has to do work and then post that data to the blockchain. And then so it's going to have to make a transaction itself, pay gas fees, all that good stuff. And then you have to wait for that transaction to be included in the blockchain. So it could take some time for this data to be posted, and boom, now it's posted. May not be instantaneous, but it can be relatively quick. And we have this volume, this big number. This is the volume of ETHUSD from cryptocompare.com. It's API. So yeah, that's in the API. Again, there's some jobs that are very specific, like maybe you want to get this weather data from Open Weather Consumer. This already helps you get set up and how to, basically a lot of the same steps, put into the Oracle job ID and requesting the weather temperature, how to do that. Also, a new feature that's really awesome and really well requested, is multivariable responses and large responses. In the past, you could only send one request and get one response back from a Chainlink node. And that response had to fit within 32 bytes or 256 bits. If it was anything bigger than that or required more than that, you would have to make multiple requests. But now there's a way we can get multiple variables with one request. This will be a great resource if this is something you want to do in the hackathon. And also large responses. If you have a very big chunk of data that you're returning back on chain, again, this will let you go beyond that 32 byte to 56-bit limit. Find existing jobs. It's going to point you to like market.link. So yeah, that is any API. This is where you can really power your smart contracts with any kind of data that may not be available as a decentralized Oracle network. Again, you can make a decentralized Oracle network if you want. And for production, that's what we want, right? We don't want to run all of our data through a single Chainlink node. We're introducing a centralized point of failure. But this can be really great for hackathon projects and for testing and generating an application that may not have an existing decentralized Oracle network without you having to go through all the effort of building one and just focusing on your application logic at first. So very handy and useful tool. All right, let's go back to the comments now. We have yes, I see there's some discussion going on. Patrick's answering some awesome questions about mocking. Yeah, so if we're gonna do this all locally, if we were to use one of those starter kits, hard hat, truffle, brownie, and we were to do this locally or even switch to JavaScript VM within Remix, those chains, there's no nodes looking at those chains because those chains only exist on our computer. No one else knows about them. So there are no Chainlink nodes, there are no keepers, there's no VRF there. So what if you want to test your smart contracts locally and but those things don't exist? You can mock these services. And in fact, these mocks have been put into our starter kits, especially the hard hat and the brownie starter kits, where you can test it that way. So you kind of just make this contract that represents the keepers, or make a contract that represents any API or VRF, and then you can act as the keeper or the any API node, and that way you get all the power of testing locally and quickly. Yes, we've got some really good questions there. Is it a way to make any API call where a TLS certification is required, and is there an automated way to keep that an up-to-date certificate? So this is going to be covered a little bit more in future demos. But nodes have this ability, if we go here, and we'll just get a little sneak peek here, and we'll go to node operators for people who want to run nodes. And there's this thing called external adapters. And external adapters allow nodes to add basically any kind of logic, customize any kind of logic the node wants, and connect it to the main node software. And within this external adapter, we can, you can put a TLS certification if you need that, any API keys, all that good stuff. We can make an external adapter and place it there. And, we can make that external adapter public, but, of course, we're not going to want to share if there's API keys, if there's sensitive information, a TLS certification with private keys in it. We may not want to share that with everyone. So we can kind of put the structure of the external adapter, but the nodes, when they run that external adapter, they'll put in their own API keys and all that good stuff. So that's how you kind of connect to these data sources how the nodes connect to data sources that require a little extra authentication. Harry's going to be running a great demo on external adapters later in the hackathon, and I'll actually be running a demo as well on running a node. So we'll cover more of these topics later. How would you make an oracle? Yeah, same thing. We're going to go over that, and I'll be actually going over that in a future demo on how you can run the Chainlink node software. Is there versioning of contracts? What if there are bugs and a new version is required? Great question. So I mean, of course, you have the Solidity. Not to confuse people, you have the Solidity version, which is up top. This just, again, tells the compiler what language of Solidity to look at. But, let's say we wanted to update our contract and go to a new contract, or change something. There's a bug and we want to update our contract and fix the bug. Remember, the blockchain is kind of immutable. That's one of the properties of the blockchain. Once we deploy something, it's really hard to change that. And so there's some workarounds this. We can make functions that allow a special address to change certain things. It's kind of a naive way. It could be very dangerous because it can give someone or a specific account way too much power over that smart contract. This could be a topic all on its own, but I really suggest looking into proxy contracts. That's how most developers today do upgradable contracts. There's a lot of nuance, a lot of detail. It could really be its own workshop. So look into proxy contracts for that. If the data is pushed to the chain, what stops you from reading Oracle API data from the chain without paying the fee? Well, the Oracle isn't just going to put the data on there. We had to send that request earlier. And to send that request, we first had to load the contract with link tokens, and then that contract is going to send the request to the node along with the link token. This is actually why the link token has its own standard, ERC 677, that inherits from ERC 20. There's a function called transfer and call. So sends all this all at once. It sends the token, it sends all the data for the request, and then the Oracle will push the data on. And if what stops other people from running it, if you make that data public on the blockchain, it'll be easy for other contracts to access it. But if hey, I need this data for my contract paid for it, you can store it in a private variable. Just a little detail there. Private variables, those determine who can access it, but everything in a blockchain is public. So even if we store that data in a private variable, if someone's running the blockchain node software, they can still dig in and find that data. It's just not going to be easy, and other contracts and other accounts won't be able to access it by default. They'll have to run a node and dive in, and be a ton of work. Okay, awesome. You guys are just coming up with great questions. Love it. All right, we're going down to the last service available for now. The Chainlink Vrf, our verifiable randomness function. So as we've seen, with Chainlink is a little bit more than just getting data off-chain, on-chain. With Keepers, we had this really cool way to automate our smart contracts and even do some off-chain computation with that check data input. But one of the more pressing needs for off-chain computation was to implement a verifiably random number generator. And so, random numbers are used all the time. A lot of times in games, if you've ever played in the lottery, where they roll the balls and stuff, trying to get a random number there. There's a good example, flipping a coin, rolling a dice. A lot of times randomness is used somewhere where we want fairness, where we want everyone to have an equal chance of being selected. And so computers have, random number generators built into them. But randomness by its nature is supposed to be something that's unpredictable, in this case, it's something that's unpredictable, hard to see what it's going to be. And generating random numbers, because of the nature that it should be unpredictable, non-deterministic, getting random numbers on chain is really, really hard, because remember, the on-chain world is deterministic. And so, like, some old school naive, like when Ethereum and smart contracts were still coming out, ways to get randomness was like to read the latest block, a timestamp and hash it, or just any on-chain hash, are connecting to making your own centralized oracle and connecting to some off-chain resource that can be hacked or manipulated. And we have those that were hacked and were manipulated. The reason using on-chain randomness is so dangerous is because while you might be using the block timestamp or anything from the block header to generate that, some on-chain hash, the miners, remember, they build the blocks. And they're going to see what that answer is before everyone else, before they transmit their block. And so they can begin, you're giving the ability to the miners to begin manipulating that randomness. So if it's like a lottery, they can say, hey, like, I'm not going to submit any block until it gets a random number that selects me the winner of that lottery. That's not what we want. So enter the Chainlink VRF. The Chainlink VRF brings a solution to bring provably random numbers to the blockchain. So we're going to, remember, this is about math-based agreements. We want to prove that what we're doing is good using math. Math is cryptography. So when a contract requests data from the Chainlink VRF, that contract can verify using these cryptographic methods that the number was indeed generated randomly. So, it generates, takes some data, it takes some seed data within itself and generates a random number and posts that on chain along with the proof. A lot of interesting use cases come from this true fair randomness on chain. Now, one common place we're seeing this is NFTs. So using randomness to create randomly generated NFTs with randomly generated stats on them. So you can prove like, hey, you built this. This is a randomly generated NFT. And actually, another demo I'll be doing later in the event, it involves this. And like NFTs, gaming, you can see a lot in games where this would be useful. Random number generators are used in games all the time to create, sources of chaos, to create fairness, all kinds of things. Maybe you're opening a digital NFT pack, and this digital NFT pack gives you skins and items for a game. You want to give your users, like, if they're going to be paying for these packs, you want to give your users the assurance that, hey, if there's a 1 in 100 chance that you get this like pretty rare sword, you want to give them that guarantee that it's actually going to be 1 in 100, that you're not manipulating it on the back end, that something shady isn't going on. So players aren't actually getting these rare items. And that's where the Chainlink VRF enables very powerful and fair applications. So let's jump right into the demo then. Same old, MetaMask, testnet ETH, and testnet Link, which we are good for. All right. And we're going to start out the docs, of course. Docs.chain.link. Say it a million times. Yeah, so we're going to go to using randomness. We'll get our introduction, explains basically how it does it. And if you're interested on like the details of the cryptography and stuff, there's some good blog posts. You can read the introduction here and kind of see how all that works. Okay, so we're just going to go ahead and jump right into it. Let's go ahead and deploy the example contract in Remix. All right, we have the import statement for this contract, which brings in the VRF consumer base. So just like Chainlink client, just like the keepers consumer, we have this contract we need to pull in. And our state, we have a couple of things here. We have the key hash and fee, which we're going to initialize in the constructor. And we have our random result, where we're going to store our randomness. So VRF and any API work very similarly. They work asynchronously. So we have to make a request and wait for a response to come back. So in our constructor, we're going to say, hey, we're taking in this VRF consumer base we're inheriting from it, and we want to initialize that contract we're inheriting from. And we're going to point to the VRF coordinator. This is like the node address in any API. This is the address of the VRF coordinator on Kovan in this case. All this detail is here. And then we have our link token address. We need to tell it, hey, this is the link token that exists on Kovan. This is the address of that contract. And we need something called the key hash, again, specific to the VRF on every location. And the fee. On testnet, the fee is set to 0.1. Link, you can always go to the docs to check what the fees are for whatever network you're on. Okay, and just like any API, we have two functions. Get a random number and fulfill randomness. Get random number, just like any API, we'll send that request out to the Chainlink VRF. We have a little require statement here that makes sure that this contract has some link tokens in it, because again, making a request, we need to pay Link to the VRF for the work it's doing. And just like any API request, after we send it, it's going to return a bytes 32, the request ID of the request that we sent out. Once that request is sent out with a link token, the VRF will compute a random number along with a proof, and the proof will be verified on chain. That'll happen in the backend, and the VRF will call fulfill randomness, put in the request ID, which should match the request ID of our request, and also give it that randomness that we requested and it calculated. We'll then take that randomness and we'll store it in our state variable random result. So I'm sure you're getting used to this workflow now. Let's go ahead and do this. Compiler isn't throwing any errors. I have it on auto compile. Let's go ahead and switch our environment to injected Web3 since we're pointing to Kovan. It is picking up Kovan, gas limit, and make sure we're pointing to the right contract. We don't want any of the ones we're inheriting here. We want random number consumer. Constructor doesn't take in any arguments. We're good. Let's deploy. Confirm. Okay, so we have a random number consumer deployed on Kovan now, and we have our functions. Again, we won't need to touch fulfill randomness, and this is actually showing up as raw fulfill randomness on this button. That's because we're inheriting from this VRF consumer base and overriding the raw fulfill randomness function. So if you're familiar with object-oriented program, that'll make sense. Basically, we're just kind of customizing it from that contract. But we're never going to need to call that. That's what the VRF is going to call. So let's look at a random result now. We didn't set it up to anything, so it's set to 0. Let's call get random number. Let's go. Yep, of course. Always, always, always got to send the link token to the contract. I forget this sometimes. Everyone forgets it sometimes. Unfortunately, the gas estimation error doesn't give you too much detail about what's going wrong. But if you see that, the first thing you should think is, have I loaded my contract link tokens It's it can be easy to forget sometimes when you're just in the midst of everything. So we'll copy our token address from here, and let's go ahead and send this contract some link tokens again. We'll paste in our address, switch it to link. We'll send 0.3 again. It's just going to do its MetaMask thing and put it at 0.299. We'll say send, confirm, and we'll have to wait for our link token to actually get included in the testnet blockchain. It's waiting in the mempool, waiting for some testnet miner to pick it up. All right, we're good. We're in. So our contract has link tokens in it now, enough to pay the fee. Everything's set up. Let's get random number. Pay our gas fee. All right. And again, if we click random result right away, it's not going to show because we have to wait for our transaction to get included. We then have to wait for the VRF to see the request, generate the random number, which it does all of those relatively quite quickly. But the real time consuming part is waiting for the VRF's transaction itself with all the data to be posted on chain. So the VRF can take some time. There's ways to get, check this out. This might take it a minute here. But yeah, while this is updating, actually, you know what? I'll just move into comments and look at questions. And when we go through, we'll come back and we'll see what the random result is. Mike. So Mike says, I don't think it's fair to charge for VRF calls. I know, it'd be cool if this could be, free and open, and anyone could just make a VRF call for free. But remember, the node is doing actually a lot of cryptographic work on the back end and computation. If we want to make a sustainable ecosystem, there's got to be a way to incentivize node operators to get to do all that work and run all that infrastructure and have that computation run. But yeah, I feel you. It is super needed function on the blockchain. Can I use Chainlink VRF from Polygon smart contracts? You sure can. It's actually very, very popular on Polygon. A lot of NFT projects and gaming projects go to Polygon because the fees are very cheap there. The blockchain is pretty fast. So if we go back to the docs, we can actually, under using randomness, we can go to contract addresses and we can see the addresses. And look, Polygon's one of the first ones that comes up. So Polygon mainnet, Polygon testnet, Binance Smart Chain, Ethereum mainnet, Kovan, Rinkeby. That's where the VRF is going. If you don't see a chain here that you want to use right now, it's constantly being integrated with new chains. Always check back in the docs. And if not, you can always deploy it. If it's an EVM compatible chain, you can always deploy it to another chain or a testnet somewhere else until the VRF is available on the chain you need. Yes, and Humanizer also says DDoS prevention. Correct. Yes, good point. These fees prevent these nodes from getting spammed. This is a big reason why fees are a thing in general in blockchain. If things are just open and free, people will and can just spam the service until it goes down, unfortunately. So by adding just a fee, it prevents them from doing that without going broke. If you don't secure millions, you can make your own random numbers on chain. It's not secure, but for low stake applications, doable. Yeah, I see your point, but I'm going to counter there and say that if it's something on chain and there's user value stored in it, that it is important. under no circumstances should we sacrifice user security to save some money. So if it's getting a little too expensive, maybe look into ways to sustainably fund your DeFi app. There's a lot of cool ideas out there. Or go to a chain where it's very cheap. On Polygon, I believe the fee is like, the fee is like 0.0001 link. So that's really nothing. You can even have the fee, it might sacrifice on UX, but you can have your users load the contract with link tokens or put that cost up to your users. Is there any danger of attack in the time between requesting and receiving random value? That's a great question. I'm definitely not a blockchain security expert. You can go really in depth with blockchain security. But I can say that, the fulfill randomness function, because it's inheriting from this VRF consumer base, it has some safeguards to assure that only the VRF calls fulfill randomness. And it checks the request IDs, make sure they matches. So, it is very, very secure to use. Amber, what's the incentive to make API calls on chain, paying for them, versus making the API calls in the JS layer of the app for free? That's a good question. So, like I said earlier, like any API, since it's using a centralized node, for the most part, you can make it where it uses multiple nodes, but that's going to take a lot of effort. Not highly recommended. But since it is going through a single node, this is not something you really want to use in production, because we don't want to have a centralized node controlling all the Oracle functions. You really want to make a decentralized Oracle network. So when you're making it on chain, when you're making an API, it's really useful for hackathon projects, for making MVPs, for where you're saying, hey, this is going to be the Chainlink node. Eventually, I'm going to put a updated, I'm going to put a decentralized Oracle network there, and they're going to be pushing data or whatever. But and it'll be more transparent too than doing it from the JavaScript layer. Remember, the blockchain is all transparent. It's all open. Everything will be there. All the logic will be there. You're not obfuscating how the Oracle functions are working behind your JavaScript app. And last, what is the Chainlink token used for? Please describe as utility. Yeah, so as we've gone through this demo, the Chainlink token is like ETH to Ethereum. It is the kind of gas-like token of the network that powers all these Chainlink nodes. It gives them the incentives to act properly. It pays them for their work, for their computation, and it prevents DDoS attacks on the nodes. Lots and lots of uses for the token within the network. You can Google all these things online. Again, the Chainlink token is not just a regular ERC20, it is an ERC677 token. So it adds in its own functionality called transfer and call that helps make all this Oracle magic happen as well. All right. Thanks for all the questions, guys. This has been fun. Let's move on. So again, summary of what we've gone over today. We talked about the Oracle problem, aka the smart contract connectivity problem, and how Chainlink solves that using decentralized Oracle networks. We talked about DeFi and how Chainlink data feeds really enable the future of really power the engine of DeFi. We need financial data for all these DeFi apps, and Chainlink data feeds aren't just price data; they can be any kind of data. We talked about how smart contracts can't just run their own functions, and how we can use keepers to automate running these functions in a decentralized way. We showed how you can access any API using Chainlink nodes and market that link. And finally, we talked about the problems of generating on-chain randomness and using the Chainlink Vrf to generate secure, provable randomness and putting it on-chain in our smart contracts. That was a lot. Now, you understand all of this stuff, and now you actually have the tools. I know I said this before and I joked around about it, but now you actually have the tools to make really powerful math-based agreements. The future of the internet and agreements as a whole, hybrid smart contracts. And I think if you haven't already, once you start doing it, it's addicting. Like you realize how much potential there is in these smart contracts and all that you can make now that you have these the Chainlink network connecting your smart contracts to the outside world. So again, if anything in here didn't make sense to you or you need to review this will be back up on YouTube. Please do take your time, go at your pace for any of the coding demos. Go back to the docs. You see I went to the docs a bunch. Go to Stack Overflow, where, ask specific technical questions. We often monitor Stack Overflow and try to answer them in a pretty timely manner. Go to Discord, have discussions, talk with engineers, ask questions there. And yeah, happy building. I hope this gave you the foundation that you needed. I hope you enjoyed this demo. I had a blast. I love teaching this stuff. So yeah, stay curious out there. And, I believe a link is being posted for a type form. If you could fill that out, that would be great. And give us some feedback on how these demos were. Be critical. Let us know. Let me know where I could have done better and what could have been made more clear for you. So thanks for listening, and congrats for completing the first day of demos. See you around in the hackathon.